But yeah, thank you for the introduction, and thanks COSIC for organizing, and also for giving me the opportunity to give a talk here. So yeah, my talk is titled Beyond Quantum Resilience, Embedded Security with and for PQC. Yeah, and the with PQC part will mostly relate to how to achieve post-quantum security for some embedded use cases, so including automotive use cases using post-quantum crypto. And then the second part and the main part of my talk is going to focus on how to achieve embedded security for PQC, so security for the PQC implementations. No, it's not working anymore. Does this still work? Okay. All right. I would have to switch on the laptop then. But yeah, very maybe useless slide here because we all know why we are here today. But yeah, as you all know, with the advent of cryptographically relevant quantum computers, then our classic public key standards will be compromised, and that's why we have to switch to post-quantum cryptographic standards, which are secure against both classic computers and also quantum computers. And what that means now, and I think Bart talked about it a lot this morning, is that we need to migrate to post-quantum cryptographic schemes. And yeah, this migration is going to be quite long, and there are different levels to this migration. So here I've put a couple of these sorts of levels, but I may be missing a few or maybe a lot of these sorts of things that have to be migrated to PQC. And yeah, so all the way at the bottom we have the crypto itself, so the schemes themselves, and then we have the implementations of the schemes, so both the hardware and the software that need to implement these schemes. We also need to migrate protocols, of course, and a lot of that work is done, for instance, in the IETF and so on. We also have to migrate the infrastructure itself, and this is where a lot of the, not just effort in terms of technical effort, but also in terms of cost is involved. And of course, we have to migrate different standards and regulations to post-quantum crypto. And what my talk is going to focus about is mostly these three levels at the bottom, so the crypto itself, and mostly implementations of post-quantum crypto, so hardware and software, with mostly a focus on how to achieve embedded security for post-quantum crypto. So we hear a lot about the challenges of deploying post-quantum cryptography on all different systems and infrastructures and so on. But when it comes to embedded devices, this is also extremely challenging. And there are quite a few challenges when it comes to using post-quantum cryptographic schemes on embedded or very constrained devices that also sometimes require high levels of security. So one of the first challenges relates to the fact that we have a few post-quantum crypto schemes standardized now, but it turns out that some of them are not really suitable for all the use cases that embedded devices need to support. And this makes it a bit of a challenge, so which scheme to use, and or even which number of schemes to support. There are, of course, challenges on cryptographic key sizes, also signature sizes. I will not go too much in the details here. Of course, performance, depending on which scheme we use, some of them are quite slow, some of them are relatively fast. Memory is also a big one for embedded devices. So initially, most of the efforts were very much focused on optimizing for speed, clock cycles, and so on. But runtime memory is quite a significant challenge for embedded devices because some of the schemes or some of the initial implementations of the schemes did use up to 100 kilobytes of runtime memory, and a lot of embedded devices don't have 100 kilobytes of memory. Sometimes they barely have 8 kilobytes of memory. And the last challenge for embedded devices or embedded implementations of post-quantum crypto is security to implementation attacks, and that includes side channel attacks and fault injection attacks. And the first challenge here is that, of course, we have to identify the different attack vectors, so the different kinds of attacks that apply to the post-quantum cryptographic schemes. And this is to first ensure that we have coverage, so that we protected the whole scheme against all possible attacks that we know of right now. And then the second challenge is designing countermeasures. So designing countermeasures that are effective, that can protect the schemes against attacks, but that are also efficient on embedded devices. And these countermeasures, so both side channel attacks and fault attack countermeasures, can have a significant performance overhead. And this doesn't really work well with constraints of embedded devices. So right now we are at a sort of nice place. We already have many standards that have been published already. So it was already mentioned during the workshop. So we have MLChem for key encapsulation, MLDSA for digital signatures, and we also have hash-based signatures, so both stateful, like XMSS and LMS, and we also have stateless hash-based signature schemes like SLH-DSA. And what's also super nice for embedded applications is that both MLChem and MLDSA are some of the best choices when it comes to embedded applications. So like I said, one of the first challenges of using post-quantum crypto for embedded applications is the fact that, of course, we cannot necessarily support all available schemes on a small embedded device. So we have to choose specific schemes to support. And some of the schemes are not necessarily useful or suitable to many of the embedded use cases. I think I will just drop this. And yeah, so some of these use cases, of course, need signatures. And in that case, we cannot simply use MLChem, like secure boot, secure update, attestations as well. There are a few examples here that require signatures where we can't use MLChem. But whenever chem is required, MLChem is quite a good choice for embedded applications because it has nice properties in terms of implementation, so efficiency. For signatures, again, like I just mentioned, MLDSA is one of the best schemes for embedded applications because it has nicer properties than the other post-quantum digital signature schemes. For the hash-based signature schemes, there are few drawbacks to these schemes which make them not necessarily suitable for all embedded applications. So for example, for SLH-DSA, signing is extremely slow. And if it's slow on the laptop, then you can imagine how slow it can be on an embedded device. And when it comes to XMSS and LMS, the statefulness is a big problem, both in terms of security and also because it has a limited number of signatures that it can produce. So the use case needs to be also limited in the number of signatures that it needs to produce. But overall, we have MLChem and MLDSA, which are overall suitable for most embedded applications. So the next challenge that I mentioned at the beginning was relating to key sizes, so both secret key sizes and public key, also ciphertext sizes and signature sizes, also speed. And yeah, MLChem is quite competitive in that respect. It's kind of a fast scheme, considering how new sort of the implementations of MLChems are. Of course, there's an increase in key sizes, but this is not so dramatic, let's say, compared to other key encapsulation schemes. So for signatures, the situation is a little bit more complicated. MLDSA can be slow, especially for signing, but it can also be quite significantly optimized. Again, signatures are larger, but of course not as large as something like SLH-DSA, where signing is also quite problematic for embedded devices. For LMS and XMSS, signing is slightly faster, well, slightly faster than SLH-DSA, and it can also be further optimized through some speed memory trade-offs. But again, the main problem with LMS and XMSS is the statefulness, having to keep track of the state and also of how many signatures we've generated. So the rest of the talk is going to focus heavily on MLDSA. Yes, FIPS 204 now, since it's been standardized. And MLDSA is a lattice-based digital signature scheme, which is based on module learning with errors. And it's one of the, like I mentioned, it's one of the schemes that is most suitable for most embedded use cases. Because it has some of these nice properties, it's not necessarily slow. Signatures are, of course, larger, but still manageable compared to some other schemes. And why MLDSA is important or migrate into a post-quantum secure scheme like MLDSA for digital signatures specifically is that digital signatures are vital to supply chain security and also automotive safety. Because using digital signatures, we can have properties or mechanisms like authentication, checking the integrity of components, using them for mechanisms like attestation on different types of architectures, and also secure boot, of course, secure over-the-air updates for both security and also efficiency. And of course, they are also used, digital signatures are also used for other purposes like traceability of components and also making sure that some components are compliant to standards, security standards or safety standards. So at the beginning when the NIST competition started, when looking at MLDSA, I think a bunch of people thought that it would be completely unrealistic to run MLDSA on an embedded device because of the runtime usage of the initial implementations. So all the unoptimized implementations, even for the lowest security level, used 50 kilobytes of RAM, and then the high security level used 123 kilobytes of RAM. And like I said, for some devices, this is completely unreasonable. Some small, very constrained devices only have 8 kilobytes of RAM or so they cannot run these types of implementations. So initially, that was the impression that dilithium or MLDSA wasn't necessarily suitable for these types of devices. But some research work that we did at NXP showed that this runtime memory can be reduced significantly. So we can go from something like 50 kilobytes to 5 kilobytes, or from 123 kilobytes to 8 kilobytes. So it's like a factor between 10 and 15 for signing in terms of runtime memory, which is quite significant. Of course, nothing comes for free. So there is an overhead in terms of performance, but which makes signing slower or verification slower, just to account for the fact that we are saving significantly more runtime memory. But these overhead are in a factor of 3 to 4, which might seem significant looking at performance only. But of course, this is because of the 10 to 15 factor on the runtime memory. And all these numbers are for software-only implementations. So this factor 3 to 4 performance overhead can be mitigated with hardware acceleration for some of the components. And what this means is that all the MLDSA or dilithium parameter sets can fit on a device which has 8 kilobytes of runtime memory, or less for the other parameter sets, for the smaller parameter sets. So what does it mean in practice to have something like MLDSA or dilithium on a relevant use case, on a real-world use case? And this is an example. This was also presented at ISCAR in 2022. It's an example of how to use MLDSA for firmware signature verification on a vehicle network processor. And these are the given benchmarks for RSA, ECDSA, and also dilithium. And in this case, there's a difference between, of course, using RSA or ECDSA or dilithium for signature verification. But overall, even though this is so fully software implementation with no hardware acceleration, the overall time for the whole installation, so verifying the signatures, mostly the big chunk of it, is 17 milliseconds, which is still manageable. And then with further hardware acceleration and so on, it's of course going to become less significant. So this shows that this is reasonable, that MLDSA can be used for these sorts of embedded use cases, even on constrained devices. And yeah, this is an example of validating a firmware signature, but the same principle applies for secure boot as well, for example. So the second part of my talk is going to focus on resistance to physical attacks. And this is the main part of my talk. And I will talk mostly about the two first types of attacks, so side channel attacks and fault attacks. Not so much about the more expensive more complicated attacks. So first of all, side channel attacks. So I'll give a little short introduction about side channel attacks, but people here from COSIC and Simula and stuff already know what these types of attacks do. But yeah, this is an attack where an adversary can observe a physical observable from a device that's running a cryptographic algorithm that's using a secret key. And the adversary can measure, for instance, power consumption, execution time, or electromagnetic radiation. And then by analyzing these measurements, they can extract information on the secret key. So that's the first type of attacks. And what I will talk about next is how to protect MLDSA implementations against these sorts of attacks. So far I've talked about how to optimize memory, how running MLDSA for firmware verification is manageable because it doesn't necessarily have that bad of a performance. But all of those examples were software only, and also without, except the last one because it was verification. So we only needed fault attack countermeasures. But in general, most implementations of post-quantum crypto or crypto in general need some form of countermeasure, either against side channel attacks or fault attacks, to make them secure for the use case that they cater to. And I'll talk a little bit more about it at the end. So, and obviously for high security devices, we need highly effective countermeasures against attacks. So how do we protect implementations of MLDSA against side channel attacks? Well, what we can use is masking, which is one of the main countermeasures against side channel attacks. And both industry and academia have investigated this countermeasure now for decades. And that's why people use it. It's because it's been investigated for so long. And what masking does is that instead of computing, let's say we have a secret value x, and instead of computing a function directly on x, we will decompose this secret value into multiple shares, in this case n shares. And then the function f will now not directly compute on x, but instead it's going to compute on the shares of x without ever revealing the value of x, or at least that's the hope, that it will not reveal the value of x. And what this requires is rewriting this function f completely so that it doesn't really apply on x anymore, but instead on the shares of x. And then at the end of this function, whether it's a cryptographic function or some other function, we need to recombine all the shares of the result to get the unmasked result, basically. And why masking is nice, or as a countermeasure, is that if it's implemented correctly, it needs to be implemented correctly and under some specific conditions on the hardware that it's running on, then it will increase the attack complexity exponentially in the number of shares that we use. And this exponential increase in attack complexity is what makes masking extremely nice. And so typically for standard, especially symmetric cryptographic schemes, usually use Boolean masking. But for something like lattice-based crypto, we use a combination of arithmetic and Boolean masking. So this diagram, I know looks very, detailed, but what it just shows is an overview of MLDSA signature generation, and then the different colored parts. So all the colored parts are essentially the secret parts that need to be protected. Whatever is not colored, for example, these parts are public or don't necessarily need to be protected. And then all the colored parts need to be protected. And then depending on which efficient version of the masking we want, or which version of masking, either Boolean or arithmetic, is best in terms of efficiency, is basically what is colored for these parts. So first of all, what we see from this is that MLDSA needs a combination of both Boolean and arithmetic masking. So this is kind of challenging for implementations to have both of these representations, because sometimes also conversions between the two representations are needed. And there are also functions that use both. So one singular function will use a combination of these two representations. So that's the next challenge. And then the last challenge that I want to mention here is the fact that, so like I mentioned before, when we mask a function, we need to kind of rewrite completely that function so that it doesn't work on the secret value itself, but instead is going to work on the shares of the secret value. And it turns out that sometimes rewriting this function completely changes what the function looks like. So, and one example for MLDSA of a function that is very challenging to mask is this decompose function, which technically, if you would look at the mathematical description of this function, it's just a division with a remainder. It's nothing really crazy. But then if you want to mask it efficiently, this is the point, is that it's masked efficiently, then you kind of have to rewrite the whole function, the mathematical description of the function, such that it computes the exact same thing as before, but instead is now more efficient to mask. And that was, and it's quite fun to work on these types of problems for post-quantum crypto or masking in general. And this function in particular was also very fun to work on. So what does it mean in terms of overhead now to deploy these countermeasures on embedded implementations of MLDSA? So this diagram shows the impact, also the clock cycles for fully software implementation, which is based on the PQM4 benchmarking library. And so if we go from something that is completely unprotected to use in 2 shares, the overhead factor is 7, which is quite significant. But then if we want to increase security from this level to the next one and then to the next one, the overhead is less significant. So what this shows is that these types of hardenings are quite expensive. Even when someone has tried to optimize them, they still remain expensive. As always, nothing comes for free. This is a security for the cost of performance. So this hardening can be expensive, but it is absolutely necessary for a lot of use cases. And if you are going to use MLDSA to achieve post-quantum security for digital signatures, for secure boot or secure updates, then it's completely pointless to ignore embedded security. Because the point of achieving post-quantum security is to protect against quantum computers. But then if these same implementations are vulnerable to side channel attacks or fault attacks that can be done with a few dollars worth of equipment, then that post-quantum security was sort of useless. Of course, this doesn't work for all use cases. If we have a server in a single server in a room, then this doesn't apply. But here we're talking about embedded devices and devices that go into critical infrastructures. And what's nice again about MLDSA, well, sort of nice and not so nice, is that for these benchmarks, 40% of the total runtime is only the side channel protected hashing, which is just used to derive some random values, basically, which could be generated some other way, not necessarily using hashing, more efficient ways. But this is what the standard describes. These values have to be generated using a hash function. Masking that hash function for this specific implementation takes 40% of the total runtime, which is not really nice for software implementations, but for hardware, so at least implementations that also use hardware in combinations, we can of course employ a protected hash accelerator to reduce this overhead further. So that was a sort of glimpse on how to protect MLDSA implementations against side channel attacks. And the next type of attacks that I want to discuss are fault injection attacks. And these ones are attacks where an attacker can sort of inject a fault through a glitch or a laser in the execution of an algorithm. And then by observing either the output or the lack of output from a device or the behavior of the device after the fault has been injected, then they can extract information on the secret key. And in this slide, I want to discuss one of the recent attacks that we've worked on MLDSA or implementations of MLDSA. And this is a fault injection attack on the sign-in procedure of MLDSA. So we'll go through the process of how the attack works, and then we'll talk about the conclusions of what that means for MLDSA implementations. So let's say we have an embedded device that runs an unprotected MLDSA implementation for signature generation. An attacker can inject a fault. And this fault is actually just a simple instruction skip. So there's a nonce increment or value increment at some point during signing. And if an attacker can skip this instruction specifically by different means, depending on the hardware, depending on the device that is being targeted, then by using the output signatures, so the faulty ones after the instruction has been skipped, and then they combine these faulty signatures with MLDSA's modular LWE problem, which is a secure problem on its own without giving extra information. But then if we give it this extra information coming from the faulty signatures, then we turn it into a much weaker problem, a ring LWE problem, but it doesn't mean that it's weaker. It's just, it's a ring LWE problem, which is significantly weaker than the MLWE problem that the lithium is based on, or MLDSA is based on. And then this problem is so weak that it can be solved using mathematical tools like lattice reduction. And then the attacker can just recover the key. Once they've recovered the key, they can just forge infinite messages, infinite signatures for all the messages they want. So this is technically a very simple attack. It's just an instruction skip. It's just skipping this instruction. This can be achieved by different means. Maybe the complicated part is this part here, but the community has done quite a lot of work on this. There are even toolboxes that are published on GitHub that you can just download to do this attack. So these attacks are extremely simple, somewhat. They're extremely simple, and that means that we also need fault attack countermeasures. So on top of side channel attack countermeasures, now we also need fault attack countermeasures. So I will not talk too much about fault attack countermeasures because typically there are a lot of ad hoc fault attack countermeasures that any implementation can employ. And usually they do not have as high of a performance impact as side channel countermeasures do. But this was again one of the fun projects that we worked on, in particular, sort of this part of turning, going from MLDSA's problem, which is secure theoretically or without additional information, into a problem that is much weaker using these faulty signatures. And we don't need that many faulty signatures here. It's a couple, it's 4 to 13, I think, if I remember correctly, the number. So it's really nothing in terms of attack complexity. So I've been talking a lot about attacks, mathematical description, Boolean masking, arithmetic masking, fault injection attacks, and so on, but lattice reduction, whatever, but what does it mean in practice? So all these types of works, so either in industry or research, so research papers on attack methods, improvements on attack methods, on post-quantum crypto, papers on countermeasures, and so on, are extremely useful and have real practical consequences. And this is because both research on attacks and countermeasures are both essential to achieving not just security, but also safety for a lot of use cases like automotive use cases. And the way this is sort of achieved, or the way this type of research trickles in, is that there's this process of certifying components or devices for specific use cases that require specific levels of security. And for instance, a manufacturer like NXP will produce a device that implements some type of cryptographic scheme along with countermeasures and so on. The manufacturer will do some in-house testing using the attacks that have been published, for instance, by the cryptographic community and other communities. They will develop their own attacks, test the product in-house. There are also other tests relating to, for instance, safety for automotive applications. There are a few standards relating to that, obviously. So there's a lot of in-house testing. And then all of this, along with the device specification and so on, gets transmitted to an independent laboratory or vulnerability lab that will basically redo these tests or even perform different tests to check that the claims of the manufacturer are correct. So both claims in terms of compliance to specific standards, this is also done, and also testing to make sure that the security claims are also met. Now, this is a completely independent laboratory. They have experts working on this, experts working on attacks and so on, and they will also run tests on the cryptographic algorithms and implementations, and that includes side channel attacks and fault injection attacks. Then when this is done, the lab will transmit the result to the certifying authority, which will basically produce a certificate that says that this particular device has been tested and it's suitable to be used for applications that require this security level, for instance. The main point is that, all these types of, all research and contribution on attacks and countermeasures will lead to us achieving both security and safety for post-quantum implementations. And it has in the last few decades, not necessarily post-quantum crypto, but classic public key cryptography, classic symmetric cryptography as well. So yeah, this brings me to the end of my talk. I want to summarize a few things, maybe a couple of things that I forgot to mention during the talk. But yeah, so the first part of the talk was about how to achieve quantum security using post-quantum crypto. I've given a few examples of how to do that for automotive use cases, for instance, firmware validation or firmware signature verification. And when we hear about post-quantum crypto migration, we hear a lot about harvest now, decrypt later, and how this is an imminent threat and we need to migrate now for applications that are sort of vulnerable to harvest now, decrypt later, which means we need to migrate chems urgently. But chems are not the only thing that needs to be migrated. Digital signatures also need to be migrated because there are devices that are in the field for decades. For instance, security components that go into vehicles that will be there, that will be in the field for decades. So signatures need to also be migrated now because they enable use cases like attestation, so making sure that the devices are secure and updated, and also secure updates to roll out not only efficiency updates, but also security updates. So we also need to migrate digital signatures now. It's not just about harvest now, decrypt later. But right now we are quite at a lucky spot because the post-quantum standards have been published. And like I mentioned at the beginning of my talk, MLChem and MLDSA, we are very lucky to have the standards already out because they are the two schemes that are the most suitable for most embedded use cases. I've also talked about some of the embedded challenges of post-quantum crypto. So there are different levels to the migration. I've talked mainly about the hardware and software or implementation challenges. There are, of course, many use cases and many applications. So yeah, this migration is going to be complicated. I've mentioned some of the implementation challenges, so memory, size, speed, and physical security. I've talked mainly about memory at the start of the presentation, so how to achieve low runtime memory for MLDSA so that it's actually possible to run on embedded devices that have very limited runtime memory. And then the second part of, the main part of the talk focused on physical attack security, or how to achieve, this time not embedded security or post-quantum security with post-quantum crypto, but instead how to achieve embedded security for post-quantum crypto. Because using post-quantum crypto alone or functional only implementations of post-quantum crypto is not going to be enough for embedded applications. And it's sort of kind of useless or counterintuitive to migrate to post-quantum crypto for embedded applications without additionally including protection against attacks, like I said, that can be performed sometimes on unprotected devices using equipment that just costs a few dollars and it's not the same cost as a quantum computer. So physical attack resistance against both side channel attacks and fault attacks, and also logical software attacks, is of course necessary for post-quantum crypto implementations, and specifically for embedded use cases and also devices that go into critical infrastructures, like for instance into automotive cars, because the whole point is that we want this security to then at the end achieve safety for the end user. Yeah, thank you so much for listening. And if you have any questions, I'd be happy to answer them.